All right, so yeah, welcome back everyone. So today we continue with the discussion of dual vector spaces. Okay, and especially we will first of all finish the proof of the theorem that we stated at the end of the previous lecture, namely the result about which linear transformations correspond to the transposition of a given matrix, right? So we would like to extend further this correspondence between matrices and linear transformations. So let's begin with recording the statement of the theorem. So this is theorem 225. Okay. So remember, we're in a situation when we have V and W, finite dimensional vector spaces. Okay, over some field of scalars F. Okay, and let beta and gamma be the respective ordered bases. Okay, now for any linear transformation T that goes from V to W, okay, we can consider the map which we denote as T with a superscript little t for transpose. So this is a map which goes from the dual of W to the dual vector space of V, and it's defined as follows. So defined by the value of this map on G is equal to the composition of two linear transformations, GT. And we define it like this for all G in the dual space of W. Okay. So recall again here that the elements of the dual space of W, W star, are themselves linear functionals on the space W, right? So it makes sense to talk about composition because the map T goes from V to W, and then the map G goes from W to F, right, as a linear functional. So this composition of functions makes sense, okay? So hence we can define our function TT like this. And the conclusion of the theorem is that then this function is a linear transformation itself, yeah, such that it satisfies that the matrix representing this linear transformation, so TT, which corresponds to the ordered basis gamma star and beta star, the duals of the corresponding bases in the original spaces. So this matrix is equal to the transpose of the matrix corresponding to the linear transformation T itself. So T, beta, gamma. Okay. So the point here is to define a new linear transformation TT, whose matrix representation is the transpose of the matrix representing T. Yeah. Okay, so we claim that this one will work. So let's note again how these maps operate. So we have vector space V, and T is a linear transformation from V to W. Then we have the corresponding dual spaces, V star and W star, and the map TT is going to go in the opposite direction on the dual spaces. Okay. All right, so let's prove this theorem. Okay. So, all right. So first of all, for any G, an element of the dual space W star, we defined the value of the map TT of G to be the composition GT. So the composition of the linear transformations T from V to W, right? And G from W to F. So this field of scalars, which as usual for linear functional, when talking about linear functionals, viewed as a vector space itself, okay? So we know that the composition of two linear transformations is itself a linear transformation, right? So hence, we have that TT of G is itself a linear transformation from V to F, right? As a composition of two linear transformations. So then we know it is itself a linear transformation. Okay, there's a question in chat. When we are using T for transpose, does this correspond to switching the entries? Yeah, so it depends on the field, yeah. So, but if the field of scalars F, then you're taking the conjugate as well, yeah. So you take the transposition of the matrix in the usual sense of transposition, which is defined for matrices with complex entries by taking the conjugation. Well, so you exchange the roles of rows and columns, right? And then take the conjugation. But yeah. Okay, yeah. All right, so, okay, so we agree so far. So the value of this linear transformation TT on, sorry, the value of the map TT on G is itself a linear transformation from V to F, okay? So it follows that TT of G is an element of the dual space of V, right? Because it's just a linear functional on V, a linear transformation from V to F. And the dual space of V consists precisely of all such linear functionals, okay? So this confirms that indeed we have that TT maps the vector space W star to the vector space V star, okay? So this map is indeed, as promised, a map from W star to V star. Okay. Next, we need to verify that this is a linear map, right? So far it's just a map. That's all we know. So let's verify that it's also a linear transformation. So given any elements GH of the dual vector space W star and any scalar A in F, okay? We have for any X, an element of V, the following series of equations. So we look at the map TT and we apply it to AG plus H, okay? So note that this is, of course, is an element of W star, the vector space W star, right? Okay. So we know that this is going to be now a functional. So it's an element of V star, right? So the whole thing belongs to V star, as we just discussed. So it is a function, in particular from V to F, right? So then it makes sense to evaluate this function on a vector X in V, right? Since the function from V to F, we can apply it to X and see what happens, okay? So first of all, from definition of TT, this is the same as looking at the function AG plus H and composing it with T, okay? And still evaluating on X. So this is just the definition of TT, okay? So, but now let's use the properties of T. So the composition is calculated by looking at the map AG plus H and evaluating this map on the value of T evaluated on X, right? Just by the definition of composition of functions. Okay, but this is equal using that T is linear. so ST is linear, this is equal to, okay, let me write it closer, sorry. So this is equal to A times G of T of X, right? Plus H T of X, right? So here I just use linearity of T, okay? But this, again, using the definition of TT, so now we collect it back, yeah? So this is the same as A times TT of G evaluated on X plus TT of H evaluated on X, right? So I just use again that TT is defined as the composition of the corresponding functions. Okay, but this, okay, so we get this, right? So this shows linearity. So hence, since X was an arbitrary element of V, we get that the corresponding functions, TT of AG plus H, so this is a function, right? Equal as a function to the function A times TT of G plus TT of H. Okay? So the conclusion is that TT from W star to V star is a linear transformation. Okay. All right. So far we have established that this is indeed a linear transformation, right? So now we have to argue about the matrix representations. So this is the second part of the proof, right? Because the conclusion, we want to say that this is a linear transformation, which moreover satisfies this condition here on the matrix representations. So next we verify this, okay? So I'm going to move to the next page, but I can go back if you need. Okay, so to look at our ordered bases that we were given. So we were given beta and gamma, right? Let us write, say, beta is x1 through xn, and gamma as, let's say, y1 through ym. Okay, so these are ordered bases. So the given ordered bases. Okay, now consider the dual bases. So consider the dual bases as defined last time. So we have the dual basis beta star, which we will write as f1 through fn, and gamma star, which we will write as g1 through gm. Okay, so these are the dual bases, which we just list in an arbitrary way, like this. Okay, so now let A be the matrix representing T with respect to beta and gamma. Okay, and as usual, when we write a matrix, we denote its entries as Aij, right? Okay. So now our task is to determine the matrix corresponding to the linear transformation TT. Okay, so to find the jth column of the matrix TT with respect to gamma star, beta star, and so since we already know that TT is a linear transformation, it makes sense to talk about this matrix, right? We know that this matrix is well defined, but now our task is actually to determine it. So to find the jth column of this matrix, we express first the vector corresponding to TT evaluated on Gj, okay, where Gj is the corresponding element of the basis. So this is an element of the dual vector space V star. We can write it as a linear combination of vectors in the basis B star, right? So we know that, again, since TT of GJ is some vector in V star, and V star is a basis, it should be, of course, possible to write it as a linear combination, right? So moreover, we want to use the properties of dual bases. So we know by theorem proved last time, so this is theorem 224, which provides us an explicit way to write a vector using the dual basis, right? So let's just use it, recall that theorem. So we can write TT of GJ as GJ composed with T, okay? So this is given by the sum S from 1 to N. We look at GJT evaluated on XS times FS, okay? So here, let's be careful what is what, yeah? So note that this whole expression, this is a scalar, yeah? So it's a scalar where, and FS is, of course, an element of the dual basis B star, yeah? So we know that each vector can be expressed with respect to the dual basis, and we know what the scalar coefficients are given by. They're given by the expressions of this form. Of course, applied in our case to the, because our linear transformation is TT of GJ, right? Which is the same as the composition, GJT. Yeah, everyone is okay with this? You're with me? Okay, so we have this, all right? So we have, we write it like this. So then we can now determine the entries of the matrix. So the row I, column J entry of the matrix representing TT with respect to gamma star, beta star is the following, because we just determined the coordinates of the vectors, right? So now we know that this is going to be GJT of Xi. So this is going to be GJ of T of Xi, the composition, right? Now this is GJ, and here we write the coordinate representation for the vector T of Xi. So we know that this is the sum K from 1 to M, A Ki, Yk, right? Because again, remember, A is the matrix representing T, right? So then when we apply T to Xi, this corresponds to multiplying it by the corresponding coefficients. So we get this, okay? Now let's apply this. So we use that GJ is linear. So by linearity of GJ, this is the same as the sum over all K from 1 to M AKI times GJ of YK, right? So we have this expression. Okay, but now let's look at what values this actually takes. So we have GJ of YK, right? So we know that this is equal to 0 if J is equal to K, and it is equal, sorry, the other way around. So this is equal to 1 if J is equal to K, and 0 otherwise, yeah? So 0 if J is not equal to K. So this is just the property of the dual basis, right? So here I'm using that as Y1 through Ym. Sorry, not the Y's, the G, right? So I'm using that the G's give me the dual basis. So as G1 through Gm is a dual basis of gamma, right? All right, so but note, so whenever K is equal to J, we get 1, otherwise 0. But then this means that the sum is actually equal to AJI, right? Because all the other entries are 0. So the only, and we get 1 for the situation when we have J is equal to K, yeah? So we are left with that, and then so this corresponds to multiplying by ji. Yeah. Okay. So we get so then we get that this corresponding entry, the ij entry of this matrix, yeah, is given simply by aji, which is the transpose, right? So then the conclusion is that the matrix representing tt with respect to gamma star beta star is equal to the transpose of t, yeah, because we get ji instead of ij. So this shows that the matrix representing this new map is the transposition. Okay, so this concludes the proof of this theorem. All right, so yeah, so this concludes the proof of the theorem. So now, since we know this, we can give a name to this map. Well, as to be expected. So definition, the linear transformation TT that we just defined in this theorem is called the transpose of T. Okay, because of its property that this matrix corresponds to the matrix representing T, we also call the corresponding linear transformation the transpose of T. And so what we have observed is that it is the unique linear transformation U such that the matrix representing U with respect to gamma star beta star is equal to the transpose of the matrix representing T with respect to beta gamma. Okay, so we have a notion of transpose of a linear transformation now. Okay, let's look at an example. So example, in some specific vector space. So define a linear transformation T from the vector space of polynomials of degree 1 with real coefficients to the vector space R square. Okay, and we define it by saying that the value of T on P of X is equal to P of 0, P of 2. So we pick two values, two real numbers, and we evaluate the polynomial at those values. Okay. So you can check easily that this is a linear transformation. I'm not going to do it, but I think you all know by now how to check such things. So this is a linear transformation. And let us take beta and gamma be the standard ordered bases for P1 of R and R square respectively. Okay. Then we can calculate the matrix representing T with respect to beta gamma. This is going to be 1, 0, 1, 2. Yeah. So you just have to evaluate it on the vectors and the bases as usual. So let's compute the transpose, the matrix of the transpose linear transformation using the definition. So we compute TT with respect to gamma star, beta star. Of course, using the theorem, we can just say it's the transpose of the given matrix, right? But let's do it from the definitions to see how the theorem actually proceeds. So from the definitions, instead of just applying the theorem to take the transpose of the matrix, yeah? So let's take, okay, so we have beta star, the dual basis. Let's write it as F1, F2. And let's write gamma star as G1, G2. Okay, and suppose that the matrix representing TT with respect to gamma star, beta star is given by some numbers A, B, C, D from F. Yeah. So we want to determine all these things. Okay, so then we have, first of all, that the value of TT on G1 is given by AF1 plus CF2, right? So we need to multiply the corresponding vector by this matrix when we apply in TT, okay? So we have that the value TT G1, excuse me, it's a function, remember? So when we evaluate it on 1, what we get is the function AF1 plus CF2 evaluated on 1, yeah? Now, by linearity, this is just AF1 of 1 plus CF2 of 1, okay? But now, since F1, F2 are the elements of the dual basis, we get that this is the same thing as A times 1 plus C times, well, let me write it. So A times 1 plus C times 0. This is equal to A, right? So we get that this value is A. But also we have that when I look at again at TT of G1 and I apply it to 1, this by definition is just the composition of the maps G1 and T, right? So I have G1, I apply it to T1, evaluate it on 1, right? So this is going to be G1 evaluated on the vector 1, 1, because that's where T sends 1, right? And this is again 1. So comparing, on the one hand, it's on the one hand we have that this is A, on the other hand this is equal to 1, right? So the conclusion is that A is equal to 1. So we have determined A from the definitions. Okay. Now we can argue similarly. So I won't do it in detail, but you can calculate it by the same idea. So similarly, okay, I don't know what I wrote here, sorry. So similarly, okay, we have that, we can determine all the other entries of the matrix. So C is equal to 0, B is equal to 1, D is equal to 2, if I'm not wrong about the calculations. And so from this, we conclude that the matrix representing T with respect to gamma star, beta star. So we have determined all its entries, right? So this is 1, 0, 1, 2. But now, this is, of course, if you compare it to the matrix corresponding to T itself, this is the transposition of that matrix, right? So this is indeed the matrix representing T with respect to beta gamma transposed as predicted by the theorem. Okay, so it's just a concrete instance of the theorem where we just did the calculations by hand. Okay, so in problems, for example, in homework, sometimes you might have to calculate these things in this manner explicitly. Okay, so this is about this theorem. Okay, so remember we also defined the double dual space. So let's figure out what's going on with that one. So I'm moving to the new page. Okay, so we consider the double dual V star star of V. Okay, so let's try to understand what it looks like. So first of all, we have the following definition. Given a vector X in a vector space V, we define X hat to be a function from the dual space V star to the field of scalars F. And we define it by saying that the value of X hat on F is equal to F of X for every F, an element of the dual space V star of V. Okay, so we define it like this. Note again that this definition makes sense, first of all, yeah, because when f is an element of the dual space, so remember it means it's a linear functional on V. So it's a function from V to the field of scalars. Okay, so in particular, it makes sense to talk about f of x. It's going to be a scalar. And so we define, and so x hat defined this way is indeed a map from V star to the scalars, to the field of scalars f. Okay, so this is well defined. Now we want to understand some properties of this map. So we have that x hat is a linear functional on V star, the dual space, right? So why is it a linear functional? Let's check it quickly. So if I have to evaluate x hat on A times f plus g, okay, where A is a scalar and f, g are elements of V star, arbitrary elements of V star, then by definition of x hat, this is the same as A times f plus g evaluated on x, right? Now here I use linearity of f and g. So this is the same as A times f of x plus g of x, okay? But now using again the definition of x hat, this is the same as A times x hat of f, excuse me. So x hat of f plus x hat of g, okay? So this shows that this is indeed linear, x hat is linear. And since it's a linear functional on V star, this means that x hat belongs to V star star, right? Which is, remember by definition, the doable dual V star star. Okay, so we see that for any x in V, we get this element x hat, which is an element of the double dual. Okay, so we have this this way to produce elements of the double dual from the elements of the space V itself. So now let's understand some properties of this definition. So first of all, we have the following lemma. Let V be a finite dimensional vector space, and let X be a vector in V. Now, if we have that X hat of F is equal to 0 for all F in V star, then we also have that X itself is equal to 0. Okay, so we have this property. Proof. Suppose towards contradiction that X is not equal to 0. Okay, then we will show that there exists some f in V star such that x hat of f is also not equal to 0. So we argue by contradiction here, okay? Okay, so first of all, choose an ordered basis, beta, which we can write, say, as x1 through xn, because the space is finite dimensional. So for V, and such that moreover, we have that x1 is equal to x, okay? So remember that any vector can be completed to a basis, yeah? If you start with any vector, we can complete it to a basis. All right, so we have such a basis beta for V. Now let f1 through fn be the dual basis for B, so B star, okay? So then we have f1 of x1 is equal to 1, right? By definition of the dual basis, f1 of x1 is equal to 1. But very important fact in mathematics, 1 is not equal to 0. Yeah, very importantly, 1 is not equal to 0. The main fact of mathematics, okay? But then we can take f to be this f1, right? And so this gives us so we have f of x is not equal to 0 as wanted, right? So this concludes the proof of the lemma. Okay. So now let's use this lemma to establish, to show that in fact we have an isomorphism between V and its double dual. And this would be the reason why there's no point to take the, at least up to isomorphism, there's no point to take, to continue taking duals. Like if I take the double dual of V, I get V itself up to isomorphism, yeah? So not equality, but isomorphism. So this is a theorem. Okay, let me switch to a new page to make sure everything fits. So this is theorem 226. Okay, so let V be a finite dimensional vector space, and we define the map. Let's call it psi. So it's going to be a map from V to its double dual, V star star, where we take the value of psi on X to be X hat. Okay. Now we claim that psi is an isomorphism of vector spaces. Okay, so we have that this is an isomorphism. Okay, let's check it. So what do we have to check that it's an isomorphism? So we have to check first of all that this is a linear map. Yeah. So the first claim is that psi is linear. Okay. So for this, let x, y be arbitrary elements of V, and let C be a scalar in F. Okay. Then for any F in V star, we have the following. So we have that the value of psi on Cx plus y, so remember it's a function, so we can evaluate it on F. By definition of psi, this is going to be simply F of Cx plus y, right? And F is an element of the dual of V, so it's a linear map. So this is equal to C f of x plus f of y, right? But by definition, this is C times x hat of f plus y hat of f, right? And this is the same as C x hat plus y hat evaluated on f. Right, so here we're using this. So hence, what we obtain is that psi of Cx plus y as a function is equal to the function Cx hat plus y hat, okay? But this is just C psi of x plus psi of y, okay? And so the conclusion is that psi is indeed linear, because we have checked the condition for linearity. Okay. All right. So this shows that psi is a linear map. Next, we need to check that it is a bijection, right? So to show that it is an isomorphism, what remains to check is that we get a bijection. So we have the second claim, B. Psi is one-to-one. Or injection, depending on what terminology you're more used to. Yeah. All right, so let's check it. So suppose that we have psi of x, and that this is the zero functional on V star. Okay, so suppose that we have this for some x in V. Okay, so let me comment here a little bit. So what do we mean by the zero functional? Okay, so as usual with linear transformations, right? The zero linear transformation is just a map that sends everything to zero. Okay, so here let me remark. So the zero functional, what it means is that psi x of f is equal to 0 for all f in v star, right? Okay, so suppose we have that this happens for some choice of x and v. All right. Then we have that x hat of f is equal to 0 for every f an element of v star, right? So here I'm just using what the definition of psi, right? So remember, psi of x is x hat. So if psi of x is a zero functional, it means it sends everything to 0. So this means by definition that psi of x of f, right? This is just the expression for that. So which is the same as x hat of f. This is f, maybe it's a bit unclear, is equal to 0. So assume this happens for every f in v star, for every functional in v star, okay? But then by the previous lemma, it would follow that x itself is equal to 0, right? So remember the previous lemma. Let me go back one page for a second. So the lemma says that if we have x hat of f is equal to 0 for all f in v star, then x itself is 0, right? All right, so now we just apply it. In this case, by assumption x hat of f is 0 for all f, so it implies that x itself is 0, okay? So what does it mean? So this means that the null space of the linear transformation psi consists of the 0 vector. It's trivial, right? We have shown that x equals 0, so 0 is the only element that psi sends to 0, okay? So this means that the null space is 0, which is the same as we know, or as was reminded in the review in the previous lectures, yeah? So we know that hence psi is 1-to-1 or injective, again, synonym, okay? All right, so we have established that psi is a linear transformation and that psi is 1-to-1. Remains to remark from this that psi is in fact an isomorphism. So psi is an isomorphism. Okay, so here we can shortcut our work a bit, yeah? Why? Because we know already that by B, psi is injective or 1-to-1, right? And also we know that the dimension of V is the same as the dimension of the double dual V star star. Yeah. Why do we know this? Well, remember, we know that the dimension of the dual of a vector space is the same as the dimension of the space itself, right? But now here we're just applying it twice because we know that this is equal to the dimension of V star. This we already know, but then the double dual is just the dual of the dual, right? So the dimension is again stays the same. So we have that the dimension of V is the same as the dimension of the double dual. But if you have an injective map between injective linear transformation between two vector spaces of the same dimension, then it's automatically bijective as well, right? So psi is also a bijection. And that's precisely what we needed to establish that it is an isomorphism. Okay, so this shows that that we get an isomorphism between the vector space V and its double dual V star star. Okay. All right. So cool. Just want to finish today with one more corollary of this result. Okay. So is it okay to move on to the next page? Or do you have any questions about this proof? Let me know. Okay, if not, let's move to the next page. So we have corollary of this theorem. So let V be a vector space of finite dimension. Okay, so the dimension of V is finite. Let V star be its dual. It's a dual vector space. Okay. Then every ordered basis for V star is the dual basis for some basis of the original vector space V. Okay. So first of all, let's make sure why this is actually a non-trivial statement. So remember, we already know that if I give you a basis for V, then we can produce the dual basis for V star, right? So remember, if I start with beta here, I can get beta star here. So we know how to start with the basis for V and produce a basis for V star. But here we actually saying the opposite question. So we start with a basis for V star, any basis for V star, doesn't matter which one. And then we show that we can find some basis for the original space V, so that this arbitrary spaces of V star that we started with is the dual basis for this basis for V that we can find. You see, so it's a reverse problem. So we know how to go from V to V star, how to move a basis from V to a basis of V star. This corollary tells us you can also go in the opposite direction. Starting with any basis for V star, we can find the basis for V for which it is the dual one. Okay, so let's prove this. And curiously, the proof has to go through the dual vector space, through the double dual. Yeah. So you'll see how it helps now. So let F1 through Fn be any ordered basis for V star. Okay. Start with any basis for V star. So combining theorems that we have proved, so theorem 224 and theorem 226, I can go back if you want to see them in a second. So combining these two theorems, we know that there exists a dual basis x1 hat xn hat in V double dual. Okay, so yeah, let's go back for a second. So theorem 26, remember, this tells us that there's an isomorphism, right? That this particular map psi is an isomorphism between V and V double dual. And theorem 224, let's see, do I have it here? It's been, okay, yeah, this was what we proved last time. So theorem 224 tells us how to express the vectors in the dual, yeah, in the dual basis. Okay, so if you think about it for a second, we can combine these two to get a dual basis in V double star. Okay, so what do we mean by this? So that is, we have that xi hat of fj, which by definition is equal to fj of xi. So this is equal to 1 if I is equal to j, and it's equal to 0 if I is not equal to j. And we have that this holds for all ij. Okay. So the point of this is that then f1 through fn is the dual basis of x1 through xn. Okay. So again, what did we do? We started with an arbitrary basis, arbitrary ordered basis of 1 through fn for V star. Then we looked at the double dual, and we used that in the double dual, we can find the dual basis for this, for f1 through fn, right? But now we know that all elements of the double dual we have they of this form. Okay, so we have a dual basis of this form, but then the corresponding x's for these x hats give us the basis of V. So this is a basis of V, right? So that the original F1 Fn is the dual of this because of this formula. Yeah, because of this condition. Okay, yeah, so all right, so this concludes the proof of the corollary. I'm going to stop here. And yeah, thanks for your attention as usual. Thanks for coming today. And I'll see you in the next lecture in the office hours. Okay. Yeah. Yeah. Thanks everyone. So see you next time. Bye-bye.